I'd like to start by thanking the organizers for this wonderful trimester. So the main idea of this talk will be a construction of a version of Dilogarithm in the algebraic situation. So let me first start with the motivation, the basic motivation behind the reason that one would expect something like that. And then I'll first talk about the complex picture for about 10 minutes, and then I'll talk about the algebraic case. So I think the main motivation was that I'll be vague in the first 5-10 minutes. So to hyperbolic manifolds of odd volume, Goncharov associated an element of K-theory, and then as the model for the hyperbolic space grew bigger, he expected that this became very close to the Euclidean space, so hyperbolic scissors class group degenerates into the Euclidean scissors class group. And then to this one, this is naturally, not naturally, but maybe similar to mixed-state motives over K, and then he expected that the Euclidean scissors congruence class groups should be similar to the infinitesimal part of mixed-state motives over K2. So in this talk, K will be a field of characteristic 0. So in fact, for this talk, only characteristic greater than 5 is enough, and then Kn will always denote Kt over t to the n. And then circle always denotes the infinitesimal part of the object. So objects like this, the close point is a retraction of things like that, so things will naturally split into two parts, and circle always denotes the infinitesimal part.
So K2 means that then the dual numbers?
Yes, K2 is the dual numbers.
It's very confusing, because the Dilogarithm also dominates K2 in the sense of K-theory.
It's like K3 and K3.
This is small K.
This is small K. No, nobody's considering K4 or K4.
There's small K.
This is small K. That counts.
K3
So that's what part I didn't get.
Sorry, so
What does the zero mean? I still didn't understand.
so it's the kernel from the this one to mixed-state motives over K. But it's a direct summation of mixed-state motives over K2. So these objects will not exist. This is only for motivation. So so this was the general picture by Goncharov, and then Bloch and Hainaut thought that one has volume map over here, and then as the hyperbolic space degenerates into Euclidean space, this volume would degenerate to the Euclidean volume, and then they expected that similarly there would be a Dilogarithm here, which extends generalizes both the Bloch-Wiener Dilogarithm and the volume map. In particular, when we scale t by a scalar, this should scale with the third power of the scale. And then they constructed such an object for the K-theory localization sequence. So Bloch originally constructed a K-theoretic version of motivic cohomology of weight 2, and they degenerated into an object which computes motivic cohomology of the dual numbers, and then construct an additive Dilogarithm in that case. So, so this is the basic background, and then I'll be a bit more precise from now. So the complex picture, so over complex numbers. So again, in this situation, everything is due to block and Goncharov. So let me start with the real analytic Chow Dilogarithm. So suppose that x over c is a complex projective curve. Suppose we have a smooth projective curve and we have three rational functions on here. Then associated to this thing we have such a two form, which is the R3. So this is a real analytic form on the.
You have too many absolute values from going, right?
This is log f1, d log f2.
You have too many absolute values. F2 and F3 are the same. So if you alternate, you would get 0. One of them, don't you want the
this
real
is
part
F2.
or the imaginary part? Yeah, but you have two terms that are the same. I think one of them should be the imaginary
yeah,
part and one the real part.
One of them I don't alternate if they're, I mean,
So alt means just
yeah,
cyclical.
yeah, exactly. If they're already
Oh,
alternating.
it's not alt, it's cyclic.
Yeah,
That's very different.
cyclical.
Alternating group is 6 elements, which includes an involution. So if you put something symmetric, you get 0. Cyclic group doesn't have it.
But this is not symmetric. This is already alternating. So I don't alternate if they're already alternating. It is alternating, really. It has. So to this object, if we integrate this two form, on here we get a real number r. So this gives a map rho r from lambda 3 cx star to r. So this might look like a bit strange, but it is similar to under 11. So it is a primitive of take the d log of everything, d log f1, which d log f2, which d log f3 in a higher dimensional object. For this one it will be 0, of course, and then take the real part of that. This is a primitive of that. So this looks a bit strange if we write like this, but it's a natural primitive. Okay, so this is the real analytic, real Chow Dilogarithm, and then if one specializes to the case when x is p1, and we look at rho r 1 minus c z with z minus a. This is the block-Wiener dilogarithm. So this is the imaginary part of v2a plus r 1 minus a. So of course v2 defines a map from the block group. So again, in this talk, block group means the pre-block group with some convention. So it's the we take strong units in C, Q vector space generated by this, modulo the 5-term functional equation for the diagram. So the main thing will be an algebraic generalization of this integral, so to say. So how to make sense of this integral in an algebraic context. So before doing that, let me say a few words about why such an object is interesting. So, if you look at the complex, the following complex, lambda 3 Cx star plus, we take all the block groups corresponding to all the points on the curve. So we have the delta map for the block complex on the first part, and then we have the residue map continues like this, and then here we can do something similar. So V2 Cx tensor Cx star. So the first map is the residue map at the closed points, and the second map comes from the block complex of weight 3. So now if, there is a map from here to R, the first component of which is the direct sum, or the sum of all the block linear dilogarithms corresponding to closed points, and the second part is the this map rho R, and then we can restrict this to the kernel, and then this factors over the image, but then the kernel over the image is the K3 of the curve, the K3 part of the K3 of the curve, and if one assumes there exists motivic shields and so on, that the Lorentz-Hare spectral sequence for the map from X to C is going to give the block variance infiltration on this one, and this will factor to the first graded quotient of the filtration, but the first part of this is H1 of C with coefficients in Q2 to R. So in some sense, this rho is a part of the regulator for the curve.
I'm sorry. Where is it, which two C of X cross comes from?
Where is it?
The right term, the very right term.
This one?
Yeah, I don't understand the not there or anything.
This is the one that did I make a mistake? You're right, I think. There is no term. Yeah.
You're absolutely right.
Mhm. Yeah. So now over K2. So now the basic situation is that we have a curve C2. So I denote it by C2, but it doesn't necessarily come from base change from K. So C2 is a smooth projective curve over K2, and I emphasize that it's not necessarily constant.
Sinan,
Yes.
could you elucidate that H1?
Right at the
Then
bottom.
what is that?
H1,
It should go to H2 of X, comma,
it's
Q,
H2,
C mod Q of 3.
Oh.
H1
H1
motivic.
H1 of motivic of C.
Okay.
So x0 is 0, then the next one is x1 with coefficients of h2 of x, but h2 of x is q minus 1. So
No, but
H1.
H1
No, no,
X,
it should
but
be
it's
3,
X.
3.
x,
There's no X on the right.
There's no X on the right hand side.
there's no x on there.
Oh,
there
maybe
X?
this is a.
This isn't, there's no x.
Oh,
There shouldn't be x
okay,
here.
you're just projecting.
Project.
Okay.
So it's so this is a filtration. So we have x1, we have x0, which is
That's a 3.
0. The next one is the graded part is x1 over mixed state modulus over C, let's say, and then it is Q0 with coefficients in H2 of x twisted with 3, but h2 of x is -1, so it's h2 of extensions of q0 with q2. So in other words, it gives an extension of motives of q0 with q2 if we have an element inside here. And if we look at the regulator of that, we get.
What is the thing in parentheses in the superscript there? K3 x, and then there's a squiggle.
Here,
Yeah,
this is 3.
that's a 3. Okay.
So let me, in this again, similar to this one, let me start by first explaining the analog of the Bloch-Wigner dilogarithm. So similar to this case, there is a map from B2 K2 to K. Let me call this Li2, and then I can explicitly write it down actually if I have an element s plus at, which is -1/2 a cubed s squared 1 minus s squared. And this again satisfies the 5-cycle relation and so on. And then the kernel of the block complex again in this case is, okay, let me write it down just in detail. If I have the block complex of weight 2, the kernel is K3 of K2 weight 2. I'll always consider Q coefficients. So by Goodwilly's theorem, this is computed by cyclic homology, the infinitesimal part. So we have this. The index is a bit strange. It's 1 less than the one indicator, and this is K. And then V2 maps to K, and similar to the injectivity of the regulators, we have injectivity in this case. So, this is cyclic homology, so it's Goodwilly's theorem. So this infinitesimal part of this one is equal to this one, and this can be explicitly computed. So this is in some sense the linear situation, which is the which gives an analog of the Bloch-Wigner. So, but then this thing is, let me first try to describe a more geometric explanation of this formula, because eventually I'd like to do things over higher moduli, and these kinds of equations become impossible to deal with. Even for this one, it is not becomes troublesome to check the sort of relations in this form. So
sorry, V2 of K2 is you take basically definition of usual V2 where you take usual 5-term relation.
exactly, yes, and you look at yeah, for any Artin ring actually, or for any local ring with infinite residue field, you can do that. You can look at symbols A such that A1 minus A is a unit in your local ring, and then you take the usual 5-term function of equation.
Okay, and how is it related to the 4-term equation for the infinitesimal version?
It's the same thing, actually. It is the same thing. It gives you that. It's equivalent. Yeah. Yeah. But for the infinitesimal one, you don't choose every element, so that's why it looks smaller. But they give the same. I mean, the cohomologies are the same for the complex.
So, what did you say about the higher? You say it's difficult or it's impossible to write down analog of this thing for higher. Well, first of all, there are two indices. There's the second block group, but they're higher block groups.
Yes.
And there's K2, but they're higher truncations.
Yes.
So can you generalize one from that?
Actually, yes. I can generalize it for both of them. If I replace K2 with Km, I can generalize it. If I replace B2 with other ones, but in that case I can generalize only with K2. And actually, there's a complicated combinatorial problem that I ran into. Actually, I sent you an email like 5 years ago, or 6 years ago. And within a day you found a fantastic generating function.
So the problem. Most stories that start with I sent you an email with and I never got any answer. Thank you for that.
But in this case, it's only with K2.
I'm sure it was me.
You don't really have to hack it so it makes a generating series.
That's right. Amazing.
So with Km, so let A to be equal to K double brackets T, and then maybe before all of this, let me say something about the zero-dimensional thing, and then I'll come back to this. Dimension 0. So rather than x is a curve, we have x as a point. So in this situation, over complex numbers, we have x, which is a rational function on a point, which is C star, and then corresponding to this, the natural object is the logarithm of the absolute value. Now, in the case over K2, suppose that again we have A over K2, which is smooth of relative dimension 0, so it's a type. But then, in this case, if we have F an invertible element inside A star, but then in this situation, A is canonically isomorphic to, so let's assume that K prime is the residue field of A. It is canonically isomorphic to K prime over K prime 2 over T squared. So I'm looking at K2 algebras. As a K2 algebra, so this is canonically isomorphic to this. So it's hard because the relative differentials is equal to 0. So it's this is in some sense the main point, that this is canonical. It's hard to overemphasize this. So once we are in this situation, we can, if we have an element alpha, if we have an element f, then we can look at K prime 2, and then over K prime T, we have this following function, which I denote by log 0, which looks something a bit stupid, but it's kind of like a branch of the logarithm. So if we have an element, then log 0, f is log of f divided by epsilon.
Can you say again what K prime is?
So K prime is the residue field of A. So now,
K with.
sorry?
Well, A is a tall over K.
No, but you also K2, so you already have a field K.
I had a field K, and then A is smooth of relative dimension 0, so this has this could have a residue field expansion.
But K2 already contains a T. It's not the same T, or is it the same?
It is the same T. T is also contained inside here, K prime 2.
Okay.
And also it's contained inside here. So now we can look at log 0 of alpha f. This is an element of K prime T K prime T, and then I have to apologize for this notation, but this is, I denote this thing by the coefficient of T inside this. So this is an element inside K prime. So this denotes the coefficient of T inside this power series. So then, the analog of log f in this case is that we take trace down to k of log 0 of alpha f, and then take the t coefficient of this. But then the thing that makes it work in dimension 0 is that there is a canonical splitting. So this situation, of course, will not happen in the higher dimensions. There will be many choices of branches, and that's going to complicate the situation. So the point will be to compare different choices of branches. So every splitting could be thought of a branch, and then how do we compare different branches? So maybe I should continue with this line now. So now we can have a similar thing, but we can do the following. If I have lambda 2 of a star, remember that this was a was k double brackets t. Maybe let me write. I think I should write it like this. And then we can go with lambda 2 of log 0 to lambda 2 of t k double bracket t, and then we can go down to k as follows. So I will call this function L. So L of a wedge b will be equal to, so we're going to take log 0 of a wedge log 0 of b, and then we are going to take the coefficient of t squared wedge t. So this will be L. Now, if we look at v2 of k double brackets t, this maps to lambda 2 k double brackets t star. Now, now from here, I can apply L and get an element inside k. But then the magical thing that happens is that this map factors through v2 k2. And then this is exactly Li2. So in order to define Li2, we just need to take the wedge of log 0 and take this coefficient. So in the higher weight and higher modulus generalization, the question becomes this part becomes a combinatorial problem about which combinations of things one should choose so that things descend down to the appropriate modulus and then gives a non-trivial function. So this again, since it coincides with the previous one, this gives an injective regulator. So the general idea in the case of algebraic geometry, so this is the linear situation, and in the algebraic geometric situation, again, the idea is to use lifting. But then there is no single lifting. So one has to choose different liftings and then compare them. So let me start with the part about how to compare different liftings. So the main idea is, let me, the one form, canonical one form, that describes homotopy. So in this situation, the setup is as follows. So we have two objects. So I have A tilde and A hat inside C1A. So by C1A, I mean these are smooth, affine A algebras. The non-curly A is K double brackets T of relative dimension 1. So again, it is extremely important that only works in dimension 1. So we have two such objects, and then we have an isomorphism chi between their reductions. So these are given. Chi is an isomorphism from maybe I should write this. Everything is A algebras, so this is again given isomorphism of A algebras. And then, so this is, and then we have the following data. We have P tilde, which is a triple of invertible functions. On A tilde, and then similar data P hat, which is a triple of invertible functions. So this is true. And then these have the property that, it's important that these objects are inside the full ring, not in their reduction, but the isomorphism is only over the reduction. And these objects have the property that if I reduce P tilde modulo T squared, now I can apply chi to this. So I apply it to each coordinate. The condition is that this is the same as the reduction of P hat.
So what does the notation mean, fixed three
It is the Cartesian product.
or product?
So it's the three functions on A tilde, which are cubed. There was already a star here.
No, but the usual notation, parentheses, and then 3, and x. So it's quite standard. No, then I think it's less confusing.
No x, no x. Just-
No x.
No x, no, just 3.
Just
Yeah,
three.
that's the notation. A squared means.
I might be wrong, but at least it's wrong the way that I understand.
Yeah, should be there.
So in this situation, we have a completely canonical map, which is
Coefficient
Omega
in the power series.
P tilde, P hat, chi, inside omega 1. So this is going to be again a bit confusing. It's going to be, so this is the reduction of this modulo T, and then the Klar differentials over K only. So it's again very important that this is only defined in relative Klar differentials. So it's a completely canonical object. So actually I should say that if one wants to, when one wants to generalize this to higher moduli, such an object does not exist in the other higher moduli. So, but one can do something else.
What do you mean by higher moduli?
When I replace 2 with m. So
Okay. Higher notations.
So now I can
So how do you
give the formula.
how do you get this omega?
I might tell you at the end of the lecture. It's going to take a bit long. So I mean the idea is, I can tell you the idea. You choose splittings of. So these are, they are all split since they are smooth by Grothendieck's theorem, and they are affine. You can always complete them modulo the closed fiber, and then they are all isomorphic to their closed fiber times the base. So choose any splittings for this, and then choose a lifting of this one. But if you and then choose the splittings so that the splittings are the splittings coincide with this one when you reduce them modulo t squared, and then you can transfer everything to the usual local coordinates, and then in that case you can give a formula for omega. But then the difficult part is to show that it's independent of all the choices. So it's independent of all the choices when you have these conditions. And in the higher moduli, it's not independent of the choices, but one has to do something else. So now I can give the formula actually. So now rho will be a map from K C2 P2 star. So I'll tell you what P2 means. So so here for P2 I need to choose a local system which lifts, okay, let me tell you what this is. So this is a collection of P to C, where C is a close point of the curve, and such that pi 2C reduced modulo t equals 0 is a uniformizer. So it's a lifting of a uniformizer for each point. So I'll call this thing a system of uniformizers. Maybe that's not a good terminology, but system of uniformizers for each point. What I want to prevent is that, and that KC to P2 star are those functions, f is in here. So first of all, this is a subgroup of the, so we take C2, and if eta is the generic point of the curve C2, so this will be an Artin ring with residue field, the field of rational functions on C. We can look at all invertible elements of this invertible elements here, and we allow only those f's such that locally at each point f is equal to pi 2 c to the some power a times some unit inside here. This is where u where u is a unit inside. Where u is a unit at the local ring at the point C. So this is not such that. So more explicitly, if we have in the affine charts, our object is going to look like this. K is t double brackets over t squared. Then we don't allow rational functions which are of this form, s divided by s plus t, for example, because this is not good at s equals 0. But we allow anything like s plus t to the power something times some something that doesn't begin with 0, or similarly, we can take s to the power something times something that does not begin with 0. That's allowed. We don't want two liftings of the uniformizers colliding. So now I can give the formula for rho. So So let's take P inside KC2 P2 star, the third power, and then okay, let me write the formula and then explain it. And then rho P is defined to be, we look at all the close points of C and then take a trace down to K of L of the residue at pi C of Q tilde C, and then at the correction term, which is the residue at C of omega of P tilde eta Q tilde C, and then with respect to the corresponding isomorphism, which I don't write. Okay, so let me try to explain this. So here, P tilde eta is a lifting is a lifting of P eta to some lifting of O C2 eta. So since this is affine, this is a lifting, and then P gives an element inside here of the third power here, and then I can lift P eta to a lifting P tilde eta on a lifting of this. And then Q tilde C's, these are for each C and C are liftings of PCs, but I have a condition on these liftings, namely they are good liftings. By good liftings I mean they are good with respect to a system of parameters that lift P2. So these can be always locally done by Grothendieck's theorem. On affine pieces we can always lift the curve and we can lift the functions. But we cannot do it over the whole curve. So we choose one rational lifting, and then for the local ones we complete everything and then choose liftings of the curve and then liftings of the functions. But then for the local ones there is a condition, we put an extra condition, we want them to be good liftings. The reason is that if they are not good liftings, then it's impossible to control the residue coming from the differential. But if we have two good liftings, then the corresponding residue of the one form can be computed. So that's the main tool. So then this formula, it turns out, is independent of all the choices. So rho is independent of all the choices and gives a map rho from lambda 3 KC2 star to K. So now this actually turns out to be exactly the same statement as an infinitesimal version of Goncharov's strong reciprocity conjecture. So let me describe the infinitesimal version. So again, maybe let me write down the statement. So if we look at lambda 3 KC2 P2 star and then B2. I did not define a block group with respect to a system of parameters, but it can be done. I don't have time to explain it. Now, over a general field, if you have a curve, then Sussman's reciprocity theorem says that if we take an element in K3, Milner Kc, and then take all the residue maps and take their sum, then we get 0. Sussman reciprocity.
K here is algebraic close, yes?
Sorry?
K here is
Yes,
algebraic
K is algebraically close. Thank you. Yes. Goncharov's conjecture in general is that, so assume that C is over K and forget all these 2's and P2's, then you have a residue map from the block complex of weight 3 over the curve to the block complex of weight 2 over the base. Now the co-kernel here is K3 and of the function field, and here the co-kernel is K2 of the base field. And Sussman's theorem says that this residue map is equal to 0, and Goncharov says that conjectures that this residue map should be homotopic to 0. In other words, there should be a map from here to here, which should make the diagram commute. So it turns out that this is actually exactly the statement as this one in this infinitesimal case. Namely, so by the infinitesimal case, I mean I look at the 0th part of this, which is the kernel of the map to B2. Sorry, there are which is the kernel of the map to the closed fiber. Now, this complex naturally splits, and then if we look at the map from D2 to here, from D2 to K, then this H is given by 2 components. So giving H turns out to be equivalent to giving a map to K with the appropriate properties, and those appropriate properties are exactly the ones that are satisfied by rho. So rho gives such a map.
May I ask a question?
Yes.
So this Milner K3 is the weight 3 part in K3, isn't it?
Yes.
And so in the previous, probably disappeared, there was the weight 2 part in K3.
Yes,
And
that's
so
here.
can you,
So that's exactly similar to the situation that I described in the beginning of the lecture. So suppose you have
so then this dotted arrow, it's going to be 0, you say?
no,
It's going to be
there is a
0.
dotted arrow which makes this diagram commute.
Okay. And then what happens if you pass down to K?
Where? To here?
Yeah?
So this is, I can go with V2 to K here.
Yeah? And then the elements coming from...
And then this is exactly rho.
That is rho.
Yeah. That's the rho that's given by here.
So your map detects element coming from weight 3 in K3?
Say it again.
Does your map detect elements which come from weight 3 in K3?
Yes, it gives a regulator from the K3C2 to here. the situation is exactly as the one in the beginning. With the, if you have an element in K3x of weight 3, that's going to give an element in x1 K0, Q0 with Q2. Now I can, maybe in the last 5 minutes, talk about the situation over higher modulus. So in higher modulus, in this case, there's again, if you look at this object, then we have, if R is between n plus 1 and 2n minus 1, so in this case there are more regulators. There's a regulator for each R between R plus 1 and 2n minus 1. And then in this situation, LR is given by given as follows. Sorry, we have this D R. And then there is a map from lambda 2 KT star, lambda 2 log 0 to lambda 2 T to K. And then this part is the same. And in this last part, one uses the function that takes the coefficients of I times T to the I R minus I. So this is between, I starts with 1 and then I is less than R minus I is greater than these two conditions. And then this gives a map, and then if you look at the map from B2A to lambda 2A star, and then compose that, this again descends through B2KM, which again gives an, if you look at the whole collection of Rs, they give an injective regulator. So in the case of algebraic cycles as well, so if we have, if we look at 2 Z1, Z2 inside the block group over the block complex of rate 2 over A, then one can use this row to define a regulator of these cycles. And then if these are smooth, if Zi, so this is the annoying condition, if these are smooth and their reductions are the same, then they have the same regulator. Then row Z1 is equal to row Z. So using these kind of things with Jin Park, we try to give a description of motivic cohomology over truncated polynomial rings. But the annoying condition is that for the regulators to be the same, we need this smoothness condition. So, Okay. In the higher modulus case, I can give a construction of the Chow Dilogarithm at the moment when the curve is constant. But I should say that the thing gives a non-trivial answer even when the curve is constant. So in particular, actually, even when the curve is P1, so suppose that C2 is equal to P1, and the functions are, again, Z1 minus C, and then we take any element, let's say S plus AT inside here. Similar to the real analytic picture, if we compute the dilogarithm of this one, we get the dilogarithm we started with. So it's this. And at the moment, I cannot generalize it to higher weights.
For questions?
As this map H which you down there,
Yes.
can't you explicitly write it down?
Yes, yes. H. So this dilogarithm, infinitesimal dilogarithm, is a splitting of this one, of this complex. So it is enough. So this is an isomorphism. This is isomorphic case. So giving H is the same as giving this map and this one. So giving H is this. So H composed with this one is equal to this. So I only need to describe what H composed with this thing is. And that's exactly equal to rho.
But the splitting is not very explicit.
It is explicit. I can give an explicit splitting. Mhm. It's as concrete as one can get. Everything is extreme.
Other, yeah,
I have a naive question. Can there be a version of a Z mod P squared in place of K2?
In that case, for the K-theories, there's no splitting. So I think one cannot expect a dilogarithm map that's defined on all of B2. So because the K-theory does not split. So there is a fundamental difference between KT over P squared and Z mod P squared. But if K is equal to characteristic P, that situation is very interesting, I think. In that case, there are, again, two regulators. One is more p-adic, and then the p-adic one, the Unver, the interesting one, is actually related to Koncevich's 1.5 dilogarithm. But in that case, in order to do something like this, it's not enough to lift to kt over t cubed. It's necessary to go to the bit vectors of k, t, and then do something over there. But Z mod P squared, I don't think.
other questions? Yeah?
Krishnan has a very nice approach to the real analytic higher polylogs via the Heisenberg groups. Is there anything similar here?
I don't know that, but maybe I can learn from him.
Other questions? Well, then, thank the speaker.